Hello, students. In this video, we're going to start studying some new concepts, and the idea is to treat problems in which forces are very short. Like we have forces that last very long, like a kick, right? Or when you hit a baseball with a bat. Those are forces that last less than a second, sometimes microseconds. So those are called collisions. And so and we want to see how to treat these forces, and then we will define a few new ideas to treat this type of problems. So one of the main ideas that we're going to discuss is impulse. And so if you look at the force here, right? So the the soccer ball is being kicked. So if you were to plot here, we have time, and then we have force here, right? So if we were to plot the force versus time, you see that it goes up, increases sharply, and then goes down. This duration here is very short. These are milliseconds. 1,000 milliseconds is a second, right? So here we have a force that lasts for a very short fraction of a second, right? And it's very, very sharp during that period. So the impulse is going to be defined as the area of this graph here. So that's the impulse force. That's the impulse, not the impulse force, sorry. That's the impulse. And so you see, if you are able to calculate this area, then you have the idea of impulse that we denote by the letter J. So one way that we can think of is that there is an average force, right, that is would give you the same area. So there is basically a square here that if you calculate the area of the square would be the same area of this other graph here, right? So that's your average force. So then you can use this idea of average force to calculate the area, and we'll see how to do that. So what is impulse? Well, impulse that we define is the area under the graph, right? So the area under the graph and is equal to that average force times delta t. So basically the idea is this. So you have here time, and then you have force. Then you have a force that is sharply goes up. Then you're going to find the average force that allows you to get that square that has the same area, that is F average, right? So that point there. And then if you multiply that by delta t, which is this here, right? So then you'll get that this quantity J, which is F times delta t, is this area, which is also equal to the area of this other graph, and that is your impulse. It's a vector quantity because the force is a vector. And so let's look at one example. Imagine that we have a force that behaves in this triangular shape. This is not a real force. Most forces will be kind of smooth, but this one, let's imagine that we have that. And these represent the force on a ball, right? So you have a bouncing ball. So you have the ground, and the ball comes up and down, right? So there is a force here acting on the ball that lasts very long. It's 8 milliseconds, and it has this shape. What is the impulse? Well, the impulse is the area of this triangle here. So the area of these triangles would be what? Would be the height, which is 300 newtons, times the base, which is 8 milliseconds, times 1/2. That's the area of a triangle, right? So that's the area of a triangle there, and then we can put in the numbers 1/2, 300, and 8 milliseconds, and we have to change this to second to make it work. So that gives you 1.2 Newton seconds, or 1.2 kilograms meter seconds. So these are the units of impulse, Newton seconds. And so if you want to do the other way around, imagine that you have the impulse and the time, and you want to find the force, then you would take that impulse divided by the time, and you get the average force, right? So the average force now is 150 newtons, which is roughly around here. So that's the average force that acted on that ball that is bouncing. So the other concept that is related to impulse is that of momentum, and this is a very important concept in physics. It goes with the idea that heavier objects have more momentum. Imagine a truck and a small car, right? A big truck, big heavy truck, right? So which one has the greater momentum? If the truck and the small, if they both have the same velocity, they both have the truck will have the higher momentum. So let's see how we define momentum. Let's start with Newton's second law. So we have the average force divided by the mass that gives you the acceleration. And the average acceleration is what? Final velocity minus initial velocity divided by delta t. So now we can combine this so we get Newton's second law here and the definition of average velocity there. So then I get that F average divided by the mass is equal to v final minus v initial, and these are vectors, divided by delta t. So I'm going to send this delta t over here and this mass over here, right? So if I did that, I get that F average times delta t is equal to mass Vf minus mass Vi. So on this quantity here, NV, and these are vectors, that we're going to call momentum. So then we get this equation, and then we define the momentum as the mass times the velocity. And the momentum is a quantity that is very important in physics, and it allows you to rewrite Newton's second law in terms of impulse and momentum. So momentum is a vector. So in 2 dimensions, I have 2 components, mass times the velocity in x and mass times the velocity in y. And so, because it's a vector, it obeys all the properties of a vector. You can add, you can subtract, you can multiply by scalars, and you can also find the magnitude of the vector. Let's look at some momentum. So we have a raindrop, a bullet, a baseball, a car, and a running person. And you can see here the masses, and we put the speed here, and then we see the momentums, right? So typical momentum, this is huge, as you would expect, because it's a car and it's going faster. And this is very small because, well, the mass of a raindrop is very small. It's this much here. And so it's this much. So you can see that the momentum is a way to combine how heavy the object is with how fast, and then you would get that quantity. So imagine a truck, right? You have a truck here, right? And let's say this truck is 5,000 kilograms, right? Going at 10 meters per second. And now imagine a small car, right? Going at the same speed, but now this car is, let's say, 800 kilograms. So it is, well, let's just make it 1,000 too. So 1/5 of the truck. So this guy has a momentum, right? So this guy has a momentum of P truck, which is equal to 5,000 kilograms times 10 meters per second. That is equal to 50,000 kilograms meters seconds. This guy has a P car, which is 1,000 kilograms times 10 meters per second. That's 10,000 kilograms meters second. So one way to think about this is this guy has a momentum that is 5 times higher than this. Or if this car hits something, it's gonna make 5 times the damage than this guy is going to make. So now we are ready to write the impulse momentum theorem. Remember the impulse that we defined at the beginning? And now we have the change in momentum. So the impulse is equal to the change in momentum. J is equal to delta P, and these are vectors. So the impulse momentum theorem states that the impulse delivered to an object causes the object to change the momentum. This is basically Newton's second law written with these two new quantities. So it's a vector equation, so it has two components in 2D and three components in 3D. And you can use it to study problems in which there are kicks and there are short forces, right? So for instance, imagine a golf ball that is being hit. So initial momentum is 0. Then you get an impulse that is given by this by the club, and then you get a final momentum. So then you get this J is equal to PF minus PI, which is the change in momentum. Or the same here for a soccer player. So you get a momentum here, initial momentum. There is an impulse delivered to the soccer ball, and then there is a final momentum. And you can see it's a vector equation here. So let's do a quick example here. We have a ball that is rolling to the right at 1.3 meters per second, and it strikes the wall and rebounds, and the velocity is 1.1 meters per second. What is the change in the ball's momentum? Well, we're going to need to find delta P and Jx. So we have, it is good to draw a picture here. We have the mass of the ball that we know, we have the initial velocity that we know, and this is what happens before. And in these problems, you always have a before and after, or an initial and final condition. And that's the key to solving these problems, right? After we have this, and remember this sign here, this sign is going to be very important. So now we write the initial momentum, right? So the initial momentum is the mass, which is 0.5 kilograms times the initial velocity. And so you get this quantity here. The final momentum is what? Is the mass times the velocity. The velocity now has a negative sign, so this is a negative momentum, right? So remember, this sign is going to be important. So now we can calculate the change in momentum, which is final minus initial. So you get the final, and then you get this minus here, right? So this minus comes from the minus in the velocity. So you get minus minus, right? So you get two negative there, they add up. So this is the final momentum. And now we can calculate the impulse, right? So the impulse is the change in momentum, which is equal to this. And so that is your impulse. So the impulse momentum theorem says that you can calculate the change in momentum based on the impulse, and that allows you to calculate the average velocity on an object. So, and then with that, you can calculate whether something will break if there is a collision or there is a quick and sharp impulse acting on the object. So let's summarize our idea. So we have the idea of momentum, which is defined as the mass times the velocity. We have the idea of the impulse, that is the force times the time that it takes for the force to act, and is basically the area on that graph. And then we have the impulse momentum theorem, which is the change in momentum equals the impulse. And with all that, you can always find an average force that gives you the same area here, and that average force gives you an idea of the force acting on an object during that time. All right, so let's stop here.